Hello everyone! In this video, we're back to writing a game of Pong in x86 assembly. That'll run from a ROM on an old 10-base-2 Ethernet card before the computer has even started booting. Since this old IBM PC XT has no drives, hard, floppy, or otherwise, this is perfectly reasonable. In a world where going to great lengths to get a game running on a 40-year-old system without just buying the missing parts right away on eBay. And speaking of, happy 40th to the IBM PC XT, which was officially released on the 8th of March, 1983. This is part 4 of a video series where I hope to put together a complete PC XT, or at least something an XT could have been upgraded to over the years. In part 1, we fixed the motherboard so it wouldn't let out the magic smoke, and fixed a corrupted ROM. In part 2, we installed a VGA card and made an adapter to make a PS2 keyboard speak the XT protocol, and played a bit with IBM Cassette Basic. And in part 3, we went through the trouble of getting the XT BIOS to run code from an oversized ROM chip in a socket on a 10-base-2 Ethernet card. If you want to be caught up with where we are now, I suggest you at least watch part 3, since that shows the tools we'll be using in this video. In part 3, we left off with just enough assembly code on the ROM to display a couple of exclamation marks before returning control to the BIOS. But that proves our code is being run, and we can move on to some more interesting code. At least if a game of Pong sounds interesting to you. We're not going for perfect, but just a quick and dirty game. So we could use the BIOS interrupts to write to the screen like we did before, but that would require quite a bit of manipulation of the cursor location, which means it would be slow. An easy way to write to the screen is writing straight to the video card text frame buffer. But before we do that, I'll have to spend a few seconds talking about 8086 segments. I'm not going to go into depth about complicated 8086 concepts. I'm certainly not an expert myself, and I expect you to look up some of the 8086 instructions yourself, maybe in the links in the description. But if you haven't done 8086 assembly programming before, the whole segments concept needs an explainer. Since the 8086, and 8088 in this case, is supposed to have 1 megabyte of addressable address space but only supports 16-bit addresses, we need a way to add 4 more address bits, and the 8086 architecture solves this using 4 segment registers, which hold the 4 most significant bits, and if you want to complicate things, another 12 bits of address that's added to the address, or offset as it's called. Did that sound complicated? Just imagine the segment as a 16-bit address that's shifted left 4 bits, or 1 nibble, to make it into a 20-bit address. The 16 most significant bits of that is what's held in each of the segment registers. To make a complete address, you simply add that to the 16-bit address the instruction is addressing. For instance, if you do like this, what happens is that we're loading the AX register with the word at the physical address E0002, since we're adding the address to the code segment register that shifted left 1 nibble. You might notice that you rarely see absolute addresses used in 8086 assembly, since the notation also takes segments into account. So you'll see the segment : offset notation, like D800 : 8002 for the address in this example. If you've heard this before and you still think it's a confusing way of doing things, then don't worry. It really is. But there are advantages to doing it this way too. Mainly the speed boost you get from having 16-bit addresses instead of 24 bits with 4 bits wasted, or something like that. The segment registers are really just 4 pointing sticks to which arbitrary 64K blocks of memory the instructions begin counting from. The segments don't have to line up with anything, or even have to be at different addresses either, and we can move them around however we want. But it's up to us to keep track of what we're pointing them at. We can't load the segments with immediate data though, so to change the segment registers we have to do something like this. And we can change it any way we want as we progress through our program. For instance, if we're changing between 2 different game states. Technically, all the segment registers can be the same, pointing to the same physical memory locations, or they can be off by as little as 16 bytes, since segment registers don't hold the last 4 bits of an address. Usually, there are very good reasons to use one segment instead of another. For instance, some instructions only support addressing a specific segment. But how does the move instruction know which segment to use as the source? It guesses. Yep, that's right. Intel thought, let's just make a default and that'll totally make sense, and if people want something else, they can precede the instruction with the segment override prefix. That can't possibly confuse anyone reading the machine language code. It's the 70s already. No one reads machine language anymore. Okay, maybe I'm paraphrasing a bit. The CPU simply has defaults for the segment of each instruction, and usually that is what you want. Since you would rarely write to a code segment address, for instance, and if you absolutely want to, you can precede the instruction with a segment override prefix like I did before when I loaded a word from the code segment into AX. So if you see 2e hex in a binary file before a move instruction, then yes, that tells the CPU you specifically want to use the code segment instead of the data segment or whatever. So, where were we? Oh yes, we wanted to put something on the screen ourselves instead of letting the BIOS do that for us. Since everyone is now hopefully caught up on x86 memory segments, we can start using our newfound powers for good. To stick with a quick and dirty approach, we can use the CGA 80 column mode, aka mode 3, which uses the color video memory at address B8000. So let's put that in a constant we can use in a segment. Since I use the ancient Intel notation, I need to put a 0 in front of hex numbers that begin with a letter. I could probably use the 0x notation for hex values, but since I don't even save a keystroke, I'm fine with giving the code an 80s look that goes nicely with the hardware. Before we write to the video RAM, let's make sure we're actually in mode 3, and after that we can worry about writing data. Since we want to write a lot to the screen, we can use the extra segment for this purpose, since it's not tied up to some other task, like making sure our code is read from the right part of memory. So if we want to write a character to the screen, we can simply do a move byte extra segment colon 0 hex and an exclamation mark. And that should put an exclamation mark in the top left corner, but since we're in color mode, the next byte over holds the color information for that character. So we need to set that too. Move byte extra segment 1 hex 20 hex. Of course, if we wanted to clear the screen, for instance, we would need a register or memory location to keep track of the character and color locations, as well as a way to loop through all the characters on the screen. Lucky for us, there's an instruction that removes some complexity and also makes this a bit faster. Remember I talked about how some instructions only work with a certain segment? Well, the store string word is one of them, and it uses the destination index to hold the current offset. Since that's a handy way of indexing into a segment, we can use that to write the character and color info to the video memory in one go. All we have to do is clear DI and write our color information in AH and blank character in AL. To clear the screen, all we have to do is repeat for each character on the screen. Luckily, the store string word instruction supports the rep prefix, so we can just load the CX register with the number of characters on the screen. And we'll let the assembler do the multiplication for us. Okay, now we should have a blank screen and we can proceed to making our game loop. I seem to recall the Atari version did all sorts of fancy things depending on how the ball hit the paddle, but since we're going for simple, let's just make the ball bounce around the screen diagonally for now. The easy way to do this is to keep track of the ball on a grid of x and y coordinates and translate that to actual screen positions for each tick. For every trip around the loop, we move the ball 1 unit in both the x and y direction, and if we hit the wall, we simply reverse the direction. To keep track of the location and direction on both axes, we need some RAM to hold our data. We need to remember to allocate and initialize the RAM later. For the x-axis, we have to remember that each character takes up 2 bytes per character. First one for the character and the second for the color. So instead of the rightmost character being 79, it's 158. If we can avoid it, we should really try not to rewrite the whole screen if we don't have to. So before we render the ball, let's clear the last known location of the ball. With that taken care of, we need to convert our XY coordinates for the ball to a location on the screen. Remember, each memory location on the screen has no concept of X, Y, or number of lines, just its offset from the color video memory base address. So to get the DI value, we multiply the number of lines down with the number of bytes per line, and then add the X value to the number of characters inward on the line, multiplied by 2, of course. Since we now have the ball location in a single register, now is a good time to save it to the last ball word we used before. Now all we have to do is define a color and shape for our ball. As you probably took my word for earlier, 20 hex is the color code for black on green, and for a ball I guess we could just use an O or an asterisk or something. But where did I get the color code from, and don't we have a better option for our ball? Once again, we're back to the technical reference manual. Section 7 not only has the character codes for special characters, but also the color codes for background and foreground. I'm not sure why, but I like the diamond better as our ball than the tiny ball character, so let's go with that. Finally, we have everything we need, so let's do a store string word to the B8000 base plus the DI register, and that should put our ball in the right spot. And if we loop around, that should give us a ball whizzing around the screen. I don't remember the last time I've written this many lines of code without at least a typo, so now is probably a good time to see if it'll assemble. And it did not. I had a feeling I forgot something. All those variables are not allocated or initialized. NASM likes to put things into sections. So to allocate a couple of locations in RAM, we should tell it where we're putting this part in the data section. And to avoid NASM padding our file and messing up the binary size, we ask it to align to single bytes instead of 16 or 8 or whatever the default. Since all this does is allocate the words and doesn't actually write anything to RAM by itself, we can just declare them all as 0. Also, since we're assembling as a flat binary, we need to pick a place in RAM to store our variables and manually initialize them. To pick a place in RAM for our variables, to start, we simply set the data segment to some reasonable place in RAM, like 2000 hex. Like I said, I'm no expert, so if you know a better or faster way to initialize the variables in RAM for a BIOS extension, I'd love to hear about it in the comments. Let's try to put the ball in the middle of the screen and have it start moving down and to the right. Okay, RAM taken care of, so let's see if it'll assemble this time. Great, no errors, and we can take a look at the binary. It looks like we're just shy of 256 bytes of game code so far. Since we're probably going to be assembling, fixing the checksum, converting it into a 64K ROM and burning it quite a few times, now is probably a good time to write a little script to do all that for us. Nothing we use here is new to this video, but I'll make sure it's in the description of this video as well. If you use Linux or macOS, everything is included with your favorite package manager. If you use Windows, I've heard a Linux shell is only a few clicks away now. Okay, now we just need to make our script executable and we can use it to assemble and burn our ROM. Wait a minute, that doesn't seem right. I think the $sign shorthand only works within the current section, which means we broke the padding when we added the data section. What we can do to fix that is to make an assembler constant for the length of each section and deduct that from the padding instead. That should work. Perfect. And the ROM is already cooking, so we'll have a look soon enough. Well, it looks like it's actually doing what we would expect. Except it's so fast that it wouldn't turn into a very enjoyable game. So now we need a delay of some sort, so we get some control over the frame rate. From the 286 PCs and onward, I believe there's a BIOS interrupt for a delay function, but I don't think that's available on the XT. Queso Fuego, here on YouTube, made a Pong game like this a while back, and his video has been a great inspiration for this one. If you appreciate good assembly programming videos from someone who actually knows what he's talking about, you should definitely check out his ridiculously undersubscribed channel. But he used the system timer to make a game loop delay, and as we'll see now, that's not going to be easy for us. If we grab the technical reference again, like we've done a few times already, you'll notice we're currently in the part of BIOS post that checks for optional ROMs and execute them. But since we're not done with post, then what's missing, you might ask? Well, not that much. If we scroll down a bit, we see the BIOS also checks the basic ROMs, does a check of attached diskette drive, which any PC floppy drive owner of the last 40 years will most likely be able to recognize the sound of anywhere. And then sets up the printer and RS-232 port, aka the parallel port and COM port if available. Finally, the horrible news for us in section 5, page 124. Enable timer and KB ints. The keyboard isn't enabled until this point, and the keyboard buffer isn't set up either. This means two things for us. First of all, we can't rely on the system timer since that won't move a single bit until well after our game is over, and the system has moved on to more important things like starting DOS 3.3. Secondly, we're in even bigger trouble since it seems we can't even rely on the BIOS keyboard interrupts to tell us what's going on with the keyboard because the keyboard buffer isn't set up. Lucky for us, we've already downloaded the solution to our delay issue since Sergey Kiselev already noticed the problem in his floppy BIOS code. He simply uses a loop that does nothing to implement a 15 microsecond loop for the XT, so we might as well reuse that. At least that looks like an easy fix for now, so let's make it a subroutine we can call. I'm not sure how Sergey's code manages to use int16 hex to read the keyboard in a BIOS extension that should work on an XT, but for now I'll just guess that that part works because it's actually executed later during boot. Or I'm completely wrong here. That's always an option. Never trust a YouTube video as a single source of truth. With our delay subroutine in place, we can just call that from our game loop. Since it's only a 15 microsecond delay, we should probably go for 1,000 of those by setting the CX register to 1,000 decimal, since that should technically give us a refresh rate of 60 frames per second. Now for the complicated part. Since we can't use the keyboard the way it was intended, we can take a look at how it wasn't intended. In section 1, page 43 of the technical reference that we're getting quite familiar with by now, we'll notice the keyboard data line goes to a 74LS322 shift register, which has the outputs connected to port A of the 8255 I/O chip. And if I'm not mistaken, I think we saw a mention of that port A earlier when we were having issues getting the keyboard to work. Back in section 5, page 90, we get a few hints that it's not impossible to read the keyboard asynchronously and a bit of code that should help us read the scan codes. And if we look at the header in section 5, page 15, we see we get scan codes on port 60 hex called KB data or port A in the BIOS code, and the control lines are connected to port 61 hex called KB control or port B. So if we just read the CPU port 60, we should get whatever is currently on the shift register. Easy. By the look of some of the other code though, the shift register stops clocking after receiving a complete scan code and needs to be cleared before receiving a new scan code. I'm not exactly sure why it conveniently stops clocking when a complete scan code is received, or why it needs to be cleared before receiving a new one, but I'm guessing it has something to do with the IRQ1 line connected to the register enable pin of the shift register. But for now, I'll take IBM's word for it and clear it using port 61 hex bit 7 before just setting it to output again. If my assumptions are off, or you can explain how exactly the 322 shift register gets the correct 8 bits from the 10-bit XT protocol, please leave a comment. Next, we need to parse the scan code. The downside of using this approach to read from the keyboard is that we don't know if we're in the middle of receiving a scan code, essentially getting junk data. If we were controlling more important things, I guess we could read the 8259 programmable interrupt controller and skip reading a scan code if it isn't ready yet, but since we'll only be looking for very few particular scan codes, basically for up, down, and quit, we'll probably be fine for now. First, we can get rid of some of the junk by eliminating every scan code with the top bit set, since that's either a release code or junk. Let's try to grab the Q key for quit and see if that works. The actual scan code listing we'll find in section 4, page 28 of the reference, but since that table only has the key number, it's not very convenient, and since the make scan codes are the same as the key number, we can just use the table on page 7 of the same section, since that includes the associated letter, for the US layout anyway. Before we get too far with handling player input, let's see if the delay works and if we can read a single scan code. Before we burn the ROM, I just need to put the quit label before the fire return, which takes us back to post. And so I don't forget the scan codes for W and S, I'll put in the branches and labels now. And then we'll see if it'll assemble this time. Looks like our assembly script worked without error, but of course there's no ROM in the programmer, so let's grab one of those and get going. Okay, it looks like all we got out of that is the same blinking cursor on a green screen we had before. I guess it's time for some debugging. I'm not really sure where to start, but let's have a look at the code and see what's up. Of course, we can start by trying to disable the cursor, as that'll give us an indication that the code has changed when we run it later. I don't really think that's the case, but maybe it's a problem we haven't defined a text section for NASM or set the alignment, but it certainly can't hurt, so let's see. Time to burn the ROM again. You might ask why I don't just use an emulator for this, and actually I did try, but it wasn't a very enjoyable experience. QEMU has very poor documentation for using BIOS extension ROMs, but I did manage to get it working. The reason I don't show it off here is that, very reasonably, it doesn't support emulating the XT hardware and clock speed. I also tried the online pcjs.org XT emulator, and that does manage to emulate a PC XT beautifully with all sorts of options, but since tinkering with the ROMs requires installing it locally and my browser cache put up quite a fight for every code iteration, it meant it was hard to know when I was running the new code and when I was running the old. Either way, it ended up taking longer than just burning a ROM once in a while. I really wish PCJS would add support for changing ROMs on the fly like it does with disks, but I guess there's just not much of a market for that feature. So here we are. I guess the fact that I have to go through burning a few ROMs doesn't make for a worse video than running the code in an emulator, since I'm the only one who has to wait for the machine to boot in real time. This little fix didn't do anything useful, but at least the cursor disappeared, so something is working. I guess the first place anything can go wrong is with the delay routine, and if I recall correctly, that does use the AX register, so probably that needs to be cleared. After another few minutes of my time, it's clear that did absolutely nothing either. I'm starting to think one of those emulators might have been a good idea after all. I don't think it's going to make a difference, but let's move the RAM initialization to the top of setup. Let's see if we can't figure out if it's the delay routine that's the problem by writing a character to screen right after that's supposed to run. Okay, still nothing. Now we can confirm by doing the same thing right before we call the delay routine. And if that works, we need to take a very good look at the delay loop. Now that we successfully get the exclamation mark with the same code before the call to the delay and don't get it after the delay, that tells us something has to be up with the delay routine or the stack, since that would also prevent us from returning correctly. Oh no. All that fuzz over a simple typo. I somehow put the instruction for jump no carry instead of jump no zero. Since the decrement will never set the carry, we're in an infinite loop instead of a short delay. Hopefully we can get a move on now. Great! Since we now have a ball whizzing around the screen, we can hopefully get our game logic working with a bit fewer issues than it took to get here. But first, let's see if we can get back to post by pressing Q. Yay! Let's get back to coding our game. One of the things I remember with mixed feelings from my first PC was the fact that it didn't have a sound card, so all I got was whatever the PC speaker was configured to spit out. In the IBM PC and XT, the Intel 8253 Programmable Interval Timer, or PIT, is responsible for controlling the speaker. We can configure it to output a square wave by sending B6 to port 43. Why B6, you ask? If we grab the datasheet for the 8253, we'll see that if we want to configure the timer mode, we have to write to address 3, or 43 in this case. And to change timer 2 to output a square wave, we have to set the control word to change timer 2 by setting the top bit to load 16 bits by setting bit 5 and 6, and mode 3 by setting bit 2 and 1, which turns out to be 10110110 in binary, or B6 in hex. Since the PIT, for reasons you'll find in the description of this video, runs at a frequency just above 1.19 MHz, if we set it to divide by 2280, we get a frequency of about 523 Hz, which on your piano would be 1 octave up from middle C. Since there's also an AND gate on the timer 2 output, we can configure it once and can simply turn it on and off when we need to, controlled by the bottom 2 bits of port B that we also use to reset the keyboard register. When we want a beep, we can simply turn on the speaker before our game loop delay, and it'll turn off afterwards, since we're already clearing those control bits. Of course, we also need to know if we're supposed to beep or not, so let's save that in a flag variable and skip enabling the speaker if that flag isn't set. Now all we have to do is set the beep flag when we hit the walls and change the direction. Let's remember to initialize the variable and see if it'll assemble. It didn't, but that just seems to be a forgotten H for hex. You might think now would be a good time to test what we've got, and you'd be right, but I'm impatient. So let's party on and write the code to handle the paddle before we get to hear the beautiful sound of that PC speaker. Since the paddle only moves in one direction, we only need to use the y coordinate value, which will be from 0 to 24, minus the size of the paddle. If up-down keys were pressed and there is room to move, we move, otherwise we skip ahead. Of course, a game like this usually also has some type of scoring, so let's check if the ball hit the paddle or not, and if it didn't, we reset the score. We could write the score on the screen and increase when the paddle is hit, but I'd like to do something simpler that's also slightly more interesting, and shows off the magnificent CGA color. Let's change the level to a new color when the score increases and reset the level when the player misses the ball. Since the color is determined by the high and low nibble of the same byte, we have to do some bit juggling, but nothing too advanced. Since we're manipulating the color a lot, now is probably a good time to give it a variable, along with the score and paddle location. To get the paddle on the screen, we also have to draw it on the screen. The last paddle variable we use to only redraw the paddle if the location changed. We just skip di ahead the number of lines down and then draw the paddle character for 5 lines. Okay, something already seems to be off. For some reason the paddle isn't being drawn, but at least we get a magnificent PC speaker beep. Half the times we're supposed to. I guess I forgot to set the beep flag when we hit the right side and the bottom. It also looks like the color changes when the paddle location's hit, but the ball location is still cleared with the wrong color. Let's see if we can get rid of some of these bugs. We can start by fixing the beeps, as that's an easy fix. I guess the paddle problem could be something in the CH register, so maybe just clearing that before we draw the paddle will fix it. It did not, but at least the beeps are fixed. But I forgot to fix the ball clearing color. Of course, we should probably clear the screen and redraw the paddle when the color changes, so let's do that, and I think I just found the issue since the clear screen routine is overriding the CX register. We can just fix that by pushing it to the stack and popping it back when we're done. Let's see if that'll assemble and take another look before we try it out. Of course, we still need to fix the ball clear color. Now that I think of it, we might as well push DI and AX to the stack as well. And remember to pop them in the opposite order. Actually, there's one more thing I'd like to add to the game that'll also make it a tiny bit easier to debug. If we add a wall for our single-player Pong, like on Leela's wrist load jack-o-meter, that'll give us another tool if something's still broken. All we have to do to make a wall is to draw a character on each line every time we clear the screen and just have the ball bounce at that location instead of the screen edge. Now let's see what that got us. It actually looks like we have a game of Pong. A slightly buggy and not very pretty game of Pong, but still, there we have it. And that's without an operating system helping us out. Even the BIOS isn't finished doing its thing. There's still quite an obvious bug where the ball clears a piece of the wall, or if this was the game Breakout, that would be a future feature. If we play a few more levels though, we'll see the game gets a bit harder than intended, as the video card is seemingly in the mode where the upper colors start blinking instead of changing intensity. I think that deserves a fix before we call it a day. If you'd like to play around with our code here yourself, you'll find it all on my GitHub, and of course there's a link in the description. For the future of this series, I just received this PCB for the Monster FDC by previously mentioned Sergey Kiselev. It's a floppy drive controller that supports up to 8 floppy drives. You heard that right. With 2 FDC ICs on the board, it'll support up to 8 drives, and even has the footprints for a serial port. I probably won't go that far for my XT here, but we'll see. Don't expect anything right away though, as the Hackaday Prize 2023 has officially started, and for this year's competition I've submitted my new project, the 65Uino. It's a 6502 based computer, very similar to my single breadboard computer, but in a very familiar form factor if you've seen some of the usual Arduino boards. The idea for the competition is that it's a relatively easy project to assemble for students and hobbyists, and does a lot of the same things the Arduino boards do, but brings the curious minds even closer to the metal by opening up the black box and separating the parts into older ICs that are easier to understand. There's certainly a video coming about that. If this video was a waste of your time, I'd love to hear what I can do better, and if you liked it, I'd certainly love a comment as well. Either way, thanks for watching.